Mehta. I'm the moderator of this session, and I wanted to welcome everybody to the National Tanks Conference and to Pittsburgh. So happy Tuesday. Our session is Site Characterization 1, Bedrock Sites. Today we have 3 speakers. They are going to do their presentations, and we will have a few minutes after that to ask any questions if you have. And then we'll have some time towards the end if there are additional questions. So our first speaker, and by the way, you all should have the session evaluation forms. If you can, please fill that out. That's very helpful for us to get your feedback. So we will appreciate your filling out that form as well. So with that said, our first speaker is Mr. Nathan Thacker, and he's a senior geologist with AST Environmental in Harrisonburg, Virginia, and with 16 plus years of environmental experience in geology and site remediation. Nathan graduated from the University of Kentucky in 2006 with a Bachelor's of Science in Geological and Earth Sciences. And he has been a full-time project manager and an engineering consulting firms in South Carolina and Kentucky, performing site assessments, design, and implementation of remedial technologies and action plans. Nathan joined the AST, the current firm, in 2013 as a senior geologist and manages most of the company's injection remediation projects along the East Coast. So with that, let's welcome Nathan for the first presentation.
Thank you, Mihir. Jump right into it. We're a few minutes late. So this presentation is going to go over our approach to not only remediation in general, but into fractured bedrock sites. Because full disclosure, I'm an injection contractor. My goal is to get in, clean up the site, get into remediation. But before we can do that, we have to identify the problem, identify that mass. And in fractured rock sites, that's finding those bedding planes and fractured rock. So our approach, you see there's different steps, and today we're going to focus on the RDC in Bedrock, which is the remedial design characterization. Really, what we're looking for in fractured rock are those bedding planes, those features that are going to transport water, transport contaminants. So we're going to use tools that are available easily, have been used for 20 years or more. We'll go over those in a little bit more detail. But we are trying to find these fractures, these bedding planes, these transport mechanisms. Before you get into going into the field, applying certain tools, our first step is always to review the literature. You see we got the GQ map up of New York. It's always good to review that literature. It's already been completed. You can find out so much about your regional geology or about your site just by reviewing that data. And that can steer you in the right direction of what kind of tools you need to apply to your site afterwards. So moving down the line, we go into surface geophysics. We apply that at sites where we need to identify better locations to place wells, injection points, depths we need to target. After we have a better idea of the faults, folds, we're dealing with flatline carbonate setting, we can get into, do we need to do rock cores? Yeah, that is a big part of cleaning up the site, is not just identifying those fractures, but in sedimentary settings, being able to characterize that rock matrix. So we want to be able, depending on the setting, we want to be able to grab some rock cores, collect samples from that matrix, and be able to identify the total mass. Once we have wells in, we can go in and do our typical borehole geophysics, which I'm sure most of you are familiar with, and we'll review those a little bit. And then once we have the fractures and bedding planes identified, then we can go in and we can grab discrete samples. So got this up here. I think most of us are one of these 3. It's got a geophysicist on the board too. He can maybe laugh a little bit, maybe not, but we'll see. I'll give you a few examples of why I find this cartoon accurate for our sites, because you really do need an expert to help you look at that geophysical data that you collect and tell you, correlate, is this really what we're seeing, or is it some sort of artifact? So this is a site, and I'm gonna go through a couple different real world sites that we worked on. throughout the East Coast. This site's in Kentucky. It's an abandoned truck stop. It's a perfect site for remediation. We don't have to worry about traffic, nice flatline geology. A little background, we have the source area up here at the pump islands and nested wells. There's some wells that are even 40 feet in length. So this is where you really need to identify the data gap. We have a very large screen interval. We need to identify those fractures and shorten up the target area a little bit. Moving down gradient, we can find this well here is boxed. It's MWU. It's always had the highest concentrations, ppm levels of benzene for 20 plus years. Another thing about this site is we had some higher impacts, shallower, and as we moved down, they got deeper. So that kind of helps. We did some research background on the GQ, and so we have some rocks slightly dipping to the south. Then we got down here, and the shallow wells had the higher concentration. So there's some sort of structure that we thought might be in place. So we ran some surface geophysics, get a better handle on the conceptual site model, see where we needed to put our injection wells, and identify, try to help us out why we're seeing this this concentration in shallower wells down gradient. So you can see we have this structure right around where MWU is, that control that really competent rock, control that groundwater flow as it goes down and then comes back up, a little upward gradient in our groundwater. So remember these purple zones that were identified in the geophysical that we're looking at the raw data, we would think is extremely weathered zone, maybe a good place to put some wells, but we'll look at some reasons why that wasn't the case. So in Kentucky, we're blessed. We have road cuts on pretty much all of our sites. So not only do you go do geophysics, but we had this beautiful road cut right here. And in wintertime's the time to go, right? So Callaway Creek limestone into the Garrett siltstone, and we could see that in the geophysics as well. Back to the electrical resistivity study, knowing your site conditions is critical. This is actually noise from underground utilities. So that's kind of going back to the little cartoon, is knowing your site conditions, having an expert geophysicist, somebody that's been doing this for a long time to help you interpret that data is really critical, because we would go over here and start chasing this weathered zone, but it's not really weathered zone. Most of you are familiar with the geophysical logs. So this is kind of a typical suite that's in the industry. Really the 3-arm caliper, natural gamma, resistivity, and fluid temperature. You're going to get that with every site. For us, the critical ones that we find help us are the televiewers and the caliper. Because as we talked about earlier, we want to find those features, find those fractures, and isolate those. Another tool that we use is a borehole camera. You'll see that there's multiple tools, as many tools as we can use. You can't use them all, but as many, multiple lines of evidence, as many tools as you can apply to a site to help you understand those features, and that structure is going to help you be able to clean up your site. It'll also help you find your scissors that you lost a few weeks ago. And then we'll get those out for you during the injection. So back to the geophysical logs. This is a site up in Connecticut, weathered basalt. We ran this like we said, typical suite, and you can see there's a lot of stuff going on, right? See some horizontal, there's some near vertical features. I'm not going to go into too much detail, but we can, if you want to talk a little afterwards, we can look at how you interpret this caliper data and see those fractures and their dip orientation. Talking about multiple lines of evidence, multiple tools. Zooming in here on this 58 to 62 foot zone, you can see there's some things going on here. Caliper is a little wobbly, shows a little bit. We got something funky going on. We got dipping 180 degrees from each other, almost vertical. But you'll see there's really nothing that stands out that, we really need to look at this feature. So after we get the geophysical results, we run our camera down. And as you can see, as we're running down, hopefully it'll stop here in just a second. We're looking at these features. We're looking for other lines of evidence of, do we need to sample this zone? Is this going to be a good zone for injection? Get there, you can see this was the gold mine right here. We didn't see this on the geophysical logs. We would have totally skipped over it because the caliper didn't really show much. But this iron staining, indicative of groundwater flow, we were able to target that during the injection. That was really the only fracture over that 50-foot zone that took any fluid, and we were able to isolate that. So I've gone over a little bit of the industry standard tools. Now we're getting into more of the specialized straddle packers. Many people have used them. You have 5-foot, 10-foot. You can put them together any way you want to, but we have worked together, AST and RPI. We have specialized straddle packers, 18-inch interval. We can inflate these to 3,000 PSI. They're very tough. This way we can get those elements to seal off the borehole, and we're only isolating that fracture that we're trying to. There's not a 5-foot zone where we're going to grab multiple features and we're going to be confused, and there's going to be questions on, do we really have the data from that fracture? So really isolating those fractures is key, getting a really good high resolution data set. Like I said, rock cores, that's another, depending on the lithology. If we're in limestone, sandstone, we want to grab those rock cores, get a better look at the fracture orientation, and be able to grab matrix samples. This is a little setup of what we do when we grab these rock cores. We can actually get a core, identify those fractures from the geophysics, and then grab matrix samples from that fracture zone. So we get the rock core out, we're able to crush it into a small 5-gram, 10-gram sample, preserve it in methanol, and we ship it out to our lab in Colorado, and we can analyze that matrix. All right, going back to our site in Kentucky, where we did grab some rock cores, like we talked about. MWU, always part per ppm levels of benzene. Let's go back real quick. BR3 is a open borehole well that we installed. We were able to go down, discretely sample features with our straddle packers. This is kind of a busy one. So this is the historical data for benzene. You see here, the highest sample that we collected from that open borehole in groundwater was 474 micrograms per liter, well below what we're seeing in the well adjacent to it. But in the rock core, we find part per million levels at 12.75 feet. We weren't able to grab a groundwater sample from there because the flow is a little too low for us to be able to grab one, but we knew we needed to inject there because that's where the mass is. This is a chlorinated site, but same process, right? It doesn't matter what the contaminant is. The process of identifying those fractures, applying multiple tools, multiple lines of evidence. We have our target well ppm levels, 26 ppm of TCE. Our open well, we weren't able to sample any of the fractures. Doesn't mean they were completely dry. Just means that the flow is too low for us to be able to sample at the time. But you can see the rock core sample at 20 feet. There's our smoking gun of where we need to inject. Another example up in New Jersey, we see dip direction to the northwest. It's pretty standard there. We have a source area down on the south of the building. Historically, multiple potassium permanganate injections in PW 1 and 2, and then induced flow from PW3. So they pumped on PW3 to induce the flow of the potassium permanganate over to these wells that had historical ppm levels of TCE. This looked a lot better on my screen, but hopefully you can see I've got the geophysical sweep run, and over to the side for each one, we have the TCE samples that we collected. So this is MW10S. We were able to go down with our packer, grab discrete samples. And then from PW3, we were also able to grab discrete samples. So we blow that up a little bit. You can see this major feature at 20, 20 and a half. At PW3, where they were pumping and they were seeing the potassium permanganate coming into the well, you see good reduction. You're at 54.8, but just 5 feet away at a monitoring well, we're still at 2 ppm of TCE. So being able to have that discrete 18-inch interval, really we're able to isolate and get a really good handle on the distribution of those contaminants in the fracture network. One more site I don't have a map for. Like I said, multiple lines, whatever we can run at a site we want to. We weren't able to run geophysics at this site. We had to go out. This well was already installed. It's historical recovery well. We were able to run the camera down before we went and sampled, identify those features and bedding planes, and then use our discrete packers. You can see this interval. If we were using industry standard packers that you can get off the shelf, we never would have had this type of resolution. Historically, the well that we're talking about has been in the 400 to 500 ppb of benzene range, no mention of LNAPL. However, while we were going down the well discretely sampling, we noticed LNAPL in a few features, which led us to go to the client and say, hey, we need to go do some rock core sampling. And possibly when we go to do the injection, we'll probably need a few more events. That is a leftover, and I got through that. So if there's any questions, I got through that pretty quick. We can talk about it now, or I'm at the RPI booth 212. I will be there all week.
Any questions for Nathan? We got 2 minutes if you have any specific questions on the presentation.
So in terms of, so you're working in composite rock, looking at the fractures, does the same apply to the salt that it would composite rock and limestone?
Absolutely. Yeah.
Just because of the porosity?
As long as that hole stays open, you can run these tools and identify those fractures and features. I mean, obviously in weather basalt and limestone, it's going to be 2 totally different fracture sets, but same tool, same process applies.
And in terms of the matrix that you're analyzing, is that comparable to analyzing unconsolidated material in terms of the culture?
Absolutely. It's exactly that's why we push for that in sites where we know there's going to be, higher concentrations and there's some porosity in that matrix, because we know that there's a majority of that mass is held up in that rock or in the soil in overburden, right? So we want to be able to understand that total mass. That way we don't underdose an injection. We don't, put in a system that's going to last for 5 years and these last for 15 years or something like that.
Is there a concern about volatile loss when you're crushing the rock matrix during the collection process?
We're very quick with it. I think that's always a concern, but it's a quick process and we get it submerged in methanol almost immediately. Yeah.
I had the same questions about the crushing the rock matrix. I mean, are you just looking for residual, contamination in that fracture zone that's,
That's going, yeah, absolutely. So, you can clean up that fracture, but if there's still mass left in that matrix, it's going to continue to be a long-term source over the years.
Okay. My other question was about the packers that you use on the straddle packers.
Mhm.
How often do those, I mean, basically, how often can you how long can you maintain those in an open borehole? Because, concern that we have sometimes is that you do a rock core and while you're waiting for, to have that evaluated and looked at, obviously you have a conduit from these impacted zones down into deeper groundwater. And we've talked about using packers as something to prevent that vertical migration while the core is being evaluated. So what's the longevity of these packers?
We don't use those packers for that.
The straddle packers,
Process.
obviously, you're right.
Yeah, we use that. Those are to walk it down, grab the sample, or we also have a set that for injection as well. There are other tools out there that you can put in a well to mitigate that vertical migration. Help me out. Flute liner. Thank you, sir.
My question is, how do you choose your locations for actual wells? Like the interval, how many do you put in? Like, you know, I can see that, you know, you're doing a good job with vertical, what's going on vertically, but then when you're doing a bedrock investigation, how do you determine how many wells are enough? You know what I mean? Because it's very complicated. There's a lot of things going on.
That's a good question. I mean, you know, it's obviously cost is a factor, right? It's super expensive to put in a bedrock well. So yeah. You know, usually when I come into it, the well network is already there. We're just helping with that vertical resolution. But yeah, you do need to step out. It's like anything. You need to step out. And if you know that's kind of going back to reviewing the literature, like what kind of fracture system are we in? Where are we going to put these wells? Where's the groundwater flow expected? You can, yeah, it's tough. It's tough because you think it's not going to be, you know, just down gradient or, you know. Absolutely. And that's why you go through that process of the geophysics, if you can, if your site allows it, the literature review, that kind of thing, for sure.
So this is pretty some advanced analytical that's coming out of your investigations. Have you had any challenges or do you have any recommendations for how you communicate that to regulators and put it into the public record for folks that, you know, are not geophysicists, et cetera, that are going to be reviewing those files later on in the site's life?
That's a good question. I don't really have a good answer for that one. You know, we try to put together a package and explain the geophysical process, what those results are, and being able to show that high resolution data. You know, we have a few visual tools that we use with 3D modeling, that sort of thing, some cross sections, but it's a challenge to be able to visualize that.
Thanks, Nathan.
Thank you.
Our next speaker is Dr. Halihan, and he's a professor in the Sun Company Clyde Wheeler Chair in Hydrogeology at Oklahoma State University and Chief Technical Officer for Estes LLC. Dr. Halihan's professional interest centers in subsurface characterization using electrical hydrogeology and sustainable water supply. He has been an associate editor for Groundwater and has served as the secretary treasurer of the U.S. chapter of International Association of Hydrogeologists. He served as the chair of the hydrogeology division and the South Central section of the Geological Society of America. And so I would like to welcome Dr. Halihan for the next presentation.
Well, thanks to COVID, I get to actually see you guys, but now there's people online too. So now I got to keep track of 2 audiences at once. We'll try to see if we can do this. I sit on the fence between 2 entities. I'm a professor. I do the things to grad students that professors do. And if you've been a grad student, you know what kind of abuse that might be. But we're making you better people. It's okay. And then I've got the commercial side where we work on problems and try to figure out real world applications. And so on the academic side, I'm either advancing the ball and getting commercialization of research, or I'm a really evil professor that's just trying to make money while I'm a professor. And on the commercial side, either I'm helpful in that I'm incorporating some research in the work I'm doing, or I'm one of those pinhead academics that is slowing down the project. And there's an old saying about the rancher that sits on the fence, ends up with a sore crotch. And after 20 years of doing this, I agree. But I sit in the middle and I deal with these things. So 20 years of electrical hydrogeology. So a lot of people are trained in hydrogeology. They get chemical measurements from wells and they say, here, we're going to assemble these chemical measurements and figure out a conceptual site model of what's happening in your aquifer, whether it's with contaminants or water supply, or you get physical measurements, or you get some different kinds of things and you look around at it. I look around electrically. And so electrical hydrogeology, we're going to take pictures, think about what it says, but we're going to do it in a way that's built to deal with some of the critiques on geophysics. And the joke on the geophysics from the last speaker, I tell that one in class pretty regularly, except for my engineer, his answer of 2 + 2 is 4.00000. So when we do this, this is a basic little gas station in Missouri. So simple carbonate site with subsurface dolines, fractures, karst features, and a headache for trying to figure out what's going on. And they poked holes, got down to about 40 foot as their basement. And they knew some things, they didn't know some things. So we went in and took pictures. Single picture is a couple K pixel camera. And so I think about it relative to digital cameras, except we're on the kilopixel camera. And then you go in and you post up your borings, you do that kind of work and you look at it. And we went in and drilled a couple locations that they brought out 55 foot of pipe. They ran out of pipe because we were showing them the spots to go. And when we drill in karst areas, we have to have a discussion with the driller so he doesn't get mad at me, because I'm going to give him the really most rotten parts of the rock. He may not be able to build a well in that location. And so he might have to come out with a pre-pack and do these sorts of things. And that's at targets. We work at anywhere from 0 to about 1,000 feet. Most of our projects are sort of 50 to 300. But we just drilled a well last week to 500 feet. And you got to tell them what's going to be happening when you're drilling an image versus drilling just a location in hard rock. A location in hard rock, you might hit a fracture. It's unlikely you're going to hit a void and have real problems while you're drilling. I've ticked off a lot of drillers, so we kind of warn them ahead of time. Here's what's going to happen to you when you drill an image. So in terms of conductivity, if you think about dirty dogs, conductive things, clay makes things a bit more conductive. Salt water makes them more conductive, and then microbes makes them more conductive. And so after looking around at these things for a long time, you can actually watch microbes growing. And most of the conductive things you see on a fuel site typically are, if they're a utility, that's one thing, but a lot of locations you're seeing microbes growing. What we don't know is what they want. And so thinking about the microbial side is tricky, because microbiologists work in a lab and they know what they want in a petri dish. But you see full grown structures out in the environment when you're taking pictures where you can see conductive microbes growing, and they have roots and they have structures that they build, very similar to watching a coral reef and thinking about why that structure of the coral reef is built the way it is relative to the way that organisms want to absorb energy and put off waste. Same thing's happening on these sites, except for we don't typically know that, but the pictures show you those things. On the resistive side is undegraded fuels, undegraded solvents, and then really clean sand or gravel. But those all make really good targets, because typically really clean sand and gravel are good flow zones. So whether it's clean or dirty, you want to know where that flow zone's at. The psychology side of this is a little bit weird, because you have to decide what targets to hit. If you hit a target, we call it biopsying. You're going to biopsy your image. If you go to the doctor and they biopsy your liver and they come back and they say, oh, it's non-cancerous, you're generally pretty excited. On the environmental side, if you come back and say, oh, your hole's clean, people think your technique didn't work. And so it's a little bit bizarre. And if it's really contaminated, and I get places that are, hey, we've been working on this thing for 30 years, there's no free product left, and I give them a huge wad of free product they didn't know about, that's a mistake too. And so the psychology of the technique, you have to walk people through the psychology before you walk through the field data, because the projects go a little strange when you get data that you think you did a great job. I just showed you a whole bunch of free product, and the client is ticked because you showed them a whole bunch of free product on a site that's not supposed to have any. So if we're going to look at features in Bedrock, I had a beautiful Pennsylvania site, nice aged, dipping and folded stuff, and the DOD said, no. So I'm going to show you a couple other sites. We're going to talk about a little bit about taking pictures of dipping features and thinking about the kinds of issues you're going to have in Bedrock. And then we'll do a scan that was after surgery. And we get a lot of those where you're looking 30 years of cleanup and it's not clean yet. Let's finally take some pictures. And then a scan before surgery of, we're in karst, we know this is gonna be a problem. Let's take the picture first and then put in our boreholes. So if we want to think about a dipping feature, you're working with a trapezoid from the surface and you're going to go shoot over some sort of dipping feature, which is probably not going to be as pretty as that. But I've got a couple photos in the subsurface that look about like that. But if we go across it, you can get the nice dipping feature running through the image. You can get that within about 5 degrees. And that's basically based on the resolution and the grid and a bunch of things like that. But within about 5 degrees, you can see that thing, so long as you are running down the dip. If we were at an angle and when you're going through a plant or across the site, we can go whatever direction we want. And a lot of times we want to try to get orthogonal to those regional features so we could try to get the best picture of them. But if we went straight along strike, now we're just going to get that there's a flat feature down there. So we've got to think about those issues. And so we take lines in different directions because you're not sure what's going to pop out of the imagery. And you got to think about that issue as you go along. Following a process is really key. And if my partner is an engineer and we've got a really big version of this that has way more steps. So if that makes you feel good about life, we can show you a picture that has tons and tons of steps. But the 5 version is taking all the historical data. That stuff's really valuable. And it told people a lot of things, even if they've been working for 30 years. And so incorporating that is critical on using these tools when you're integrating them together. You don't just say, I'm going to go collect stuff with my tool, because you're going to see different results than you did with other tools. Whatever kind of tool you use, you will get a different view of the site, whether you're in the borehole or whether you're at the surface. So integrating that stuff's critical. People think going out and taking the pictures is the end of it. That, hell, well, you took the pictures and you understand what's happening on my site. No. And they say, well, I've already got 700 wells, so you don't need to take any more wells. No more data is required. You just take your pictures and you'll tell me what's happening. If your site was that clear, you probably didn't call me, especially for these sites. Every site I've got is started in 1994. I don't know. 1994 is magical. But so you go out and scan, then you can start doing the real hard work. You integrate and figure out what things don't make sense. Then you do confirmation biopsies and prepare people to deal with the social side of the psychological of what if we find a lot, what if we find nothing at a particular location. And it's the hardest step of the world is the psychology of those results as to what comes back. The science of it makes sense. The I don't understand psychology very well. Then you end up with a CSM where you've married these pieces together and you have a pretty good understanding of what's happened on a fuel site. The other thing you have to do is break these apart. And so you build a geologic CSM. You take these data sets and go, okay, where are the rocks and which parts of those rocks are important? Is it a particular fracture? Is it a particular bedding plane? And you got to separate that out and get that sorted out before you go down into the contaminants. And people want to run right into the contaminants. And it's like, well, hold up. Let's figure out where our rocks are at first. And that's really critical on these bedrock sites. The hydrologic CSM, we get a lot of perched water tables and things. And so do we understand what's happening with that and what things are going on that make this bedrock site a little weird? Are our fractures connected? Are our fractures not connected? Are there karst tubes that are connecting then to fractures? I've had all these different combinations, so you got to work that out. And then we've got to work out the bioactivity, and electrical pictures show you conductance that very commonly on fuel sites corresponds to where the bioactivity is occurring. And so sorting that out a lot of times changes what the remedy might be. And we've taken images of sites that were fresh, yet they were completely moldy and infected. And it was fantastic from the perspective of degradation, but it wasn't the original plan. And so it changes and you go, why don't you just guys do an M&A on this or a natural source zone depletion, because you got so much activity. And there's places in the world that happens that you wouldn't expect. And then you finally get to the CSM for where the contaminants are at. The end result, you've got an integrated conceptual site model. You put these tools together, but you got to step through it. So we're going to look at a truck stop here. Began in the 90s. They took out 7 different USTs. They got about 70 wells in the site, and it's just not cleaning up. So went into 2020. This is a sandstone siltstone of the Garber Wellington in Oklahoma City. So this formation has lots of different grain size changes, lots of different sedimentological structure, and then it's fractured. And the fractures aren't necessarily clean, aren't necessarily easy to see because it's a teenage rock. It's not really all that well cemented. So if we look at a single image, some things that show up is conductive side, we're looking at probably getting microbially active. And so this range down in the purple is getting too conductive for being just sort of normal stuff. And then resistive, this black, it's too resistive for fuels on a normal site. Normally resistors for fuel are up above 250, but not typically over 1,000. And we see these sorts of things. And if we sample in them, we get methane bubbles. And so the same as you get a natural gas deposit in an oil field, we get natural gas deposits on our fuel sites, but we normally can't see them. And they show up as a resistor that's too high and it's a gas bubble. And so we got to think about not just a PID, but an FID while we sample those locations to see, is that a methane pocket? And if we look at the distribution of resistors across here, the plume is here in the red. This is a mound spring, but it's a dead mound spring. So you get weird things on a bedrock site. And then a lot of our resistors are up in the vadose zone and not in the plume, directly in the plume area. And so do we target those? They're up above where we've been doing our sampling. They're resistive in the range we'd expect for fuels, but do you go target those, and how do you target them, and do you avoid casing them off relative to the water table? If we look at the conductive side, the conductors are also avoiding the plume, and this has been remediated for a long time, but if you look at the sulfate, there's no sulfate left in this site. And we're in the sulfate range for ORP, and they basically have sucked out all the sulfate. We got a microbiologist playing with this site a little bit now. And we can see that the activity, there's a bunch up gradient, and then there's spots around that things are blooming, but most of the interesting area in the middle is devoid of new microbial life and signatures showing up. And so they've been sampling and looking at that, but you're watching the growth patterns and how they go after a fuel site. So the conceptual model ends up, we could detect fractures, and there's these bigger fractures in deep purple, there's smaller fractures in the lighter one. This main guy running through there ends up being a great target for remediation and for sampling. But we found these vadose zone impacts. That's your remaining free product. And we found that they were up above the water table. And if you didn't case off the above in the vadose zone and left it open, we could watch NAPL running into our wells, and we could go after that. But if you didn't know that, and you just said, we're going to go put in a well, we're going to look at the water table, case off the vadose zone, you wouldn't know about that problem sitting up above you. And basically they didn't know about it. So once we did the confirmation drilling, reintegrated that, now we've got a set of targets that they've gone back in and targeted these resistors up in the vadose zone and are cleaning out the remaining NAPL. But it gives you the location and it gives you the idea, but you have to work through that process. Here's a different site. This is Cambrian Ordovician carbonates, and this is the entire casing of the previous water supply well. You don't need any more casing than that because this is miles away from any source aside from the AST used to run the pump. They didn't want to pay for bringing three-phase power out to this site. They've subsequently paid for three-phase power to come out to this site. There was an incident where they had filled up the fuel tank over the winter. It was designed to run it in the summer when they needed excess water, and things happened and drained the entire thing past the secondary containment onto the ground right next to the municipal supply well with that much casing. So they have 6 foot of diesel in their municipal supply well in a karst setting at 100 feet down. So decided to then image it. We did the scans to figure out the distribution, remediated it under 2 years. The whole thing's non-detect. And that's the kind of way we want to go after our sites is, hey, I know this is complicated. This is fractured. This is karstic. And we want to be able to deal with that and get this kind of result where, yep, we had to go clean it. We had to do those things. And so we've done that and we've cleaned it up and left. And that municipal supply well is now back online. Set up a set of images based on the depths we were trying to look at. This also has a perched water table at about 30 feet. But looking at targeting the remediation, we were trying to figure these things out. And this was talking to the driller. And the driller said, I've never seen such rotten rock in this aquifer. Like, because you didn't get lined up to the spots that were rotten. And so trying to build wells in these locations, this is not a highly karstified aquifer. This is mostly a fractured dolomite. So you've got fractures, but you don't have like big holes all over the place like some of the other limestone karst areas. but we could still give them spots that were causing them trouble while they're drilling. And so dealing with that is something you got to go on with a driller and try to make sure that they're okay with the fact that they might need to deal with the installation a bit differently, or they're going to get locked up in the hole or not have the stuff to build the well. And working with that is actually a bigger hurdle than I expected in some regards. And when we map these out like this, they're trapezoids. So we put the ends of the trapezoids so we can see where we're getting loss of depth and then the full depth of the image, and making sure we're going across the site in a way that's useful for the depth objectives. We're going to look at this line right across the source area. So our well is sitting over here with our tank system. The tanks are no longer there. There's now a nice 3-phase power line. And if we look at that, there's an excavation pit that they did when they first spilled. And you get a resistor down below that. And then you get these conductors off to the side. And this is the surface topography going this way. And you say, okay, well, you've told me I could have conductors or resistors. Which one is it? I'm not sure. I'm definitely pretty suspicious of a resistor underneath a fuel tank. Definite target. But hey, is this strong conductor sitting down gradient? Is that have the microbes started growing and eating your fuel already? It's diesel, so I don't know. It's not my first guess, but it's something we should check into. So, and then to give you a scale, I put a couple giraffes, so the right scale. These pictures are always trapezoids, and this might be 1,000 foot deep. So I sometimes forget to tell you what depths we're working with. So this is, and a giraffe is 5 meters for those that haven't used giraffes as depth scales before. If you do the drilling and you go into the conductor, it's non-detect. It's not a big flow zone, and it's a little bit of a flow zone, but there's no diesel has made it from there over to here. It didn't run down through this epikarst and get into this part of the system. And you can then map out the geology, and you've got a soil, and then you've got an epikarst, and then you get into the bedrock. There's more structure in the picture, but you can get the idea that the picture is similar to what the drilling's showing you. If you go into this resistor that kind of heads down into the municipal supply well, and you go into this one underneath the excavation tank, you get some dissolve phase here and you get some free product there. And so it's lining up. It's a nice fresh site, and you haven't had 3 remediations electrically that you have to look through while you're trying to figure out your picture. So it's a little easier if you're going into the beginning because there's not other stuff that's been altering the electrical properties in the ground. So put in some free product recovery wells. Those are dealing with the perch system as well as some of the system down at depth. But then we can also take a picture over time. And the same way you can do hydrogeology, you can put in a well and watch chemistry over time or watch water levels over time. You can watch electrical things over time. And this one, after remediation, has gotten really conductive around there. And when you look at some of the data we were getting, the microbes are growing and eating the little remnant stuff that was around, and they were blooming. And so we can watch that growth and decide what it means for us as far as trying to deal with the site. So 20 years of taking pictures of fuel sites, done probably over 100 fuel sites with this technology, and looking at way weird sites that people are going, we've been stuck on this one. And you take the pictures and you figure out what's going on. But these impacted sites, they're a dog's breakfast. There's 3D flow paths, there's biogeochemical reactions, there's stuff going on that make them more complicated than something like a nice sand site. But if it was a nice sand site, I probably wouldn't have got a phone call. So scanning, you get the targets, and then you get a really useful conceptual site model. And using wells, I've got sites where you couldn't imagine they could perforate it anymore. And I still go, your target's between those two. And they go, okay, and you drill it and you give them feed a free product, and they go, well, how does that work? And it's like, our targets aren't that big in the subsurface. You got to do something to target them, and using a vertical well is not going to do it for you. So you end up with cheaper and focused remediation, and that's what you want out of life. In the future, we're going to do some things like they do for seismic, of thinking about attribute analysis. And we've been starting to do that in some of our bedrock sites, of figuring out the orientations of fractures and setting them up in 3D, and then doing the temporal work. And so instead of ERI, we call that TERI, and setting up TERI monitoring stations and setting up a monitoring well. And you get 1,000 foot of data instead of 2 inches. And so quite useful for looking at a site long term. So any questions, I'd be happy to answer them. And even if you're a cat person, I'll take questions.
So you mentioned as an example, a scenario where you have microbial activity, there was consumption of the available sulfate. So you had obviously some sulfitogenesis. So if you were to do a scan across a hypothetical zone where you had that typical like classic redox zonation that we always see, would the scans be able to resolve in like high mineral soils difference from like oxidized minerals to those that have been impacted by like reduction through sulfitogenesis?
So as far as we can tell, it depends on what they're doing. So like a guy doing oxygen looks similar to a guy doing nitrate on electrical basis, but a guy doing sulfate reduction or methanogenesis, those guys look similar. And so you can separate those guys out if they have a nice structure. But like working on an old refinery, they'll have structures built and then they'll have like 100-foot long route going down doing something where you have a structure that extends the depth that's not contaminated. It's part of the biological structure, but those forms are something that we're trying to work with microbiologists and figure that out, because it's like looking at, this is the old elephant problem of they've been looking at elephant pieces and I'm seeing trunks and legs and going, what do they do with the legs and what do they do with the trunk? And the microbiologist going, I didn't know they had one. And so trying to work out some of those forms, we figured out how to sample the forms better in terms of being efficient, but in terms of what they're doing and what it means, there's a lot of work to do on the biological side.
Just a quick question. I know this is a Bedrock focus. Does the technology work sort of equally as well in unconsolidated formations, silt sands, gravels? Yeah.
Sure, you're passing electricity through, so we've gone everywhere from loose sediments through competent granites and going from salt flats to dry terrains.
Yeah, I noticed in one of your first slides, you had some of the aspects of the built environment. Were you able to utilize any of that in remediation activities?
In terms of thinking
Like
about
utility lines and.
Yeah, so we that's step one. You bring in all that information, and we don't avoid utilities, but you try to. It actually is not great for seeing a lot of modern utilities. A lot of modern utilities electrically are fairly well isolated from the subsurface, so we don't have big conductive utilities anymore. Some of the old utilities can be, but if they're rusted, they're not great. But we incorporate that into the 3D, so you can think about utilities both from a perspective of, are you seeing a utility versus a target, and from the perspective of, you don't want to poke a hole through a utility. And we've had a case where we saw a nice big conductor and said, you have some sort of utility. I wouldn't poke the hole there. They're like, you have a great big conductor and we know there's no utility there. We said, we're just warning you, it photographically looks like a utility. And they set up the rig, and quite fortunately, they set it up at the same time that the city engineer was driving to work, pulled the car off the side of the road and started running to them to stop them from hitting the city water main. So you could see these things and you do have to think about it, and all the same things when you're going in invasive and doing your biopsy, you got to be careful.
Thank you, Todd.
Thanks.
All right, so our final speaker today is Mr. Dale Wickmeyer, and Dale is a research geophysicist with the US EPA Office of Research and Development. He performs basic and applied research on the geophysics response to contamination, remediation, and conceptual site model development. He also provides technical support and guidance to the US EPA regional offices, state and tribal governments. So let's welcome Dale.
Thank you. Thank you very much. So if you've had enough geophysics, you should leave. So let me see if I got this working. Okay, so the outline of today's talk, I'm going to go through why you'd want to use geophysics if you haven't learned before. Obviously, as you said, I'm a research geophysicist, so I'm going to give you 3 good applications of using geophysics. I'm going to try to move through those pretty quick on how you can use geophysics at a site or a lust site. And I'm going to hopefully get to this stuff and dive in a little bit deeper into some conceptual site model development using geophysics, and then some resources that we have at the EPA to help you learn more about geophysics and some tools that are available as well. So why geophysics? If you haven't learned, right? So from the two previous talks, prior to, if you're going to have surgery, you're going to get an X-ray and an MRI, right? So before you drill a hole, you might want to figure out what's under the ground. Just as Todd just said, you don't want to hit a utility, so let's figure out what's there. In case the city engineer isn't driving by, you can know what's under the ground. So each geophysical method, I'm going to go through a lot of different methods here. They all measure a different physical property. Okay, just like we use an X-ray to find bones and MRIs to get soft tissue in the earth, in the body, we can use different geophysical methods that I have listed here, like electrical resistivity that you've heard about already, or ground penetrating radar, electromagnetic induction, or whatever, to measure the electrical properties in the ground. Or we can use magnetic methods and even other EM, electromagnetic induction methods, to understand the magnetic susceptibility of materials under the ground. And there's a whole suite of different methods, but these are the main ones I'm going to talk about, in addition to using different seismic methods to understand density contrast in the subsurface and how that might relate to the different materials under the ground that we might run into. So first off, let's look at using trying to find underground storage tanks or some utilities, right? So I'm going to show you a couple examples here. This one on the left, this is the same gas station, a truck stop. There's a building here, everything's labeled there. And on the left, this is a map of the total magnetic field intensity. And that's collected with this instrument here. There's two different sensors, one on the top, one on the bottom. And what this is really measuring is the intensity of the Earth's magnetic field, and how that magnetic field is accentuated or attenuated based on the physical properties under the ground. So you can see that, we've got all sorts of highs and lows. This is the dispenser island. This is the truck area, but things are kind of muted. This is an underground storage tank here. There's a couple back here. But you can see we don't really get bullseyes because this figure right here shows that the anomalies we find are typically on the inflection point of that response. We can also go through this whole site and survey it with this EM method. So the EM methods work where we send a primary electromagnetic wave into the ground, and based on the physical properties of the ground, we get a secondary EM wave. So if something's really conductive, that secondary wave will be stronger. If it's really metallic, it'll also be strong. So here you can see, and we get two components when we use this instrument. One is essentially like a really high-tech metal detector, where we look at the ratio of that primary and that secondary wave. And then we can also calibrate the instruments to measure the bulk ground conductivity, the electrical conductivity of the subsurface. So you can see, as you look at the mag data, compare it to the two EM data, you can see the EM data really helps isolate things. You can see some utilities sliding in here, the dispenser islands here, but we also found this big blue blob, which was not evident at the subsurface, and that turned out to be an old building foundation where they used to change oil. So of course, well, here's an unknown area where we need to further investigate. You can also use GPR. Maybe you're very familiar with this, to find tanks. These are typically what we get. We have different antennas, different sizes, gives us different resolution and depth of penetration under the ground. We can further refine. Here's a couple of tanks. We can get really good depth estimates of where those are. And we get reflections that come back based on the electrical properties and also the metallic properties of the subsurface. We can also use geophysics, as you've seen before, to map contaminant plumes. Now, this isn't from a leaky underground storage tank. This is from a really big leaky well. From the Deepwater Horizon spill, we were able to do some research at a barrier island here. As the plume floated on the island, here you can see the resistivity section, and here's our high resistivity that shows. And here we can see we dug down, not very deep, but it's in pretty conductive soils, to where we can see, okay, here's our electrically resistive hydrocarbon. And whenever you look at DC resistivity surveys in the absence of clay materials, the governing equation that really governs your response is called Archie's law, where what we measure, the resistivity of the earth, is directly proportional to the resistivity of the pore fluid. Okay, and then it's also related to the geology, the degree of saturation and so forth. But here you can sort of see that, oh, okay, here we've got some fresh hydrocarbon, which is, it's the fluid making up the pore space, so it's electrically resistive. So our measurements is resistive. We also instrumented this site and measured it over about a 15-month time period. We had solar panels and everything, and it survived until a storm came. But basically, you can see here's what I showed you before. Here's the resistivity plume, the oil plume. And as time goes on, you can see that high resistivity just sort of move through that island, and over time it's gone. Now there's still some residual left, but it gives us an idea of how we can use a DC resistivity method to monitor that plume migration. And as Todd alluded to, or spoke a lot about the sort of the biogeochemical response to microbial degradation. This is another site, and this is some of the work that sort of started some of the research in that area. But here's sort of the opposite, right? Previously, I showed you, here's our resistive hydrocarbon. Well, here's an area where it's conductive. And we took some samples and ran some experiments and put some downhole instruments in, and we can see that we have a big conductive zone, pretty coincident with the sort of the LNAPL smear zone. We also looked at the geochemistry. You can see that where there's free LNAPL, we have a big high increase in calcium and dissolved inorganic carbon. And also working with biologists, we can see that, at the contaminated site, here's all the alkane degraders that are chewing it apart. So we see that the geophysical response over here, this conductive zone, is coincident with the geochemistry and the biology. So this response is coincident with those microbial changes. So that's sort of what Todd was talking about before. We can also use geophysics to monitor active remediation. This is a soil vapor extraction system that we were able to monitor using 3 different geophysical methods. This first one is called self-potential, which is a method where we measure just the Earth's natural voltage potential in the subsurface. That's without injecting a current like DC resistivity is. And here you can see there's these red blobs which correspond with the plume. And this is before the soil vapor extraction system went in. You can see about 11 years later, those red blobs are gone, and our SP, our self-potential anomaly, doesn't exist anymore. We also did some DC resistivity there, and here's our elevated conductivity or our low resistivity where the plume is. And you can see about 6 years later, that's getting smaller, and then 11 years later, after the SVE system's been functioning, we get sort of a natural or background normal geological distribution in the subsurface. We also looked at this with GPR, and you can see, maybe you can't, but up here, these reflections is that energy, that radar energy is going into the subsurface. If there's something's conductive there, it's going to absorb all that energy. So we're not going to see those reflections very well. We can see when the plume was fresh, those reflections are really muted. And then over time, as it gets cleaned up, we can see really nice, strong reflections that come through. And this is the water table in here. So that's an example of using geophysics to monitor active remediation. Okay, so now we're going to get to dive in a little bit deeper for using geophysics for some conceptual site model development at 2 different sites. This is down in Havasu Landing, which is south of Las Vegas. So here's Las Vegas. We're going down the Colorado River, and there's an old hardware store that had a underground storage tank that leaked, and that's the plume. There's also another underground storage tanks that have been removed here, and we're right by the lake, and we're in sort of a predominantly unconsolidated lithologies, alluvial lithologies, and the water table's less than about 6 meters in depth. So we came in to this site, and as I said, I'm a research geophysicist, so we throw it all at it. It's a total shotgun approach. Like, let's see what different instruments respond, because again, we're trying to measure the physical properties of the earth and how those might be altered either through the presence of contamination, the presence of different objects, or any sort of biogeochemical alterations that might be happening. So we went through, here's the magnetometer again. Remember I showed you that. We've got 2 different sensors, and we'll GPS tell us where we're going. We use 2 different electromagnetic induction instruments. One's a GEM2. You can see it right here. And this is the same as before. Remember, it sends out a primary wave, and we get a secondary wave that comes in. And this is a dual instrument. This is the long yellow one. It takes two people to carry around unless you have a cart. But here we can see a little bit deeper because the coils where the energy goes in are a little bit further apart. We did some radar here and then some resistivity. And we also use this little instrument right here, which I'll get into, which is a passive seismic instrument. And we did a bunch of borehole logging. And I'm not going to read that to you, but this is all the different methods and what you can use them for. And again, I think that what I want to stress is that, these aren't plume locators. We're not out here, we're measuring the physical property changes in the subsurface, and what they might be attributed to is what these instruments respond to. Just like when I described Archie's law, right? Where Archie's law was related to what we measure physically is the geology and the pore fluid and those factors that change. So what did we do? We went through and we walked all over the site with those surface instruments. You can see our lines here in yellow. And we did one big resistivity line all on the back of the site because the plume that we were aware of was going off in this direction. You can see all the holes that we logged as well. So this is the magnetometer results, okay, similar to what I showed you before from one of the first sites with the mag and the two EM responses. So here we can see, and we do this first because we want to figure out what utilities might be under the ground and what other objects might be under the ground that might influence our geophysical methods, but also because utility trenches are often highly permeable and can, be a preferential flow direction for any fluids that might be moving in the subsurface. So it's a good idea to know where your utilities are and different things underground. So anyway, you can see where things are located there and what we use that for. What's neat too, we can also do some processing, some sort of fancy, geophysics wizardry, because, we just want to give you the picture you want, right? And Nathan liked that one. So anyway, we can look at the vertical gradient, which is basically looking at the first vertical derivative of the magnetic response. And what that does is that removes any regional magnetic responses and accentuates the near surface features, which is what we're concerned about at a UST site. We can also downward continue those data. And what you can really see is you can see that what we have here is there's in fact, I probably should have showed you this previously. I'm going to go back, but we can see where there's underground utilities and different objects that we see on the surface. And when we start looking at the data deeper, we can see, oh yeah, look at that. There's a nice utility trench here. You can really see the foundation of this building here. This is an above ground storage tank. And what's interesting, you may notice or you may wonder like, well, why isn't this, if this is a utility trench, why isn't this like a nice straight line of anomalies, right? Because this is magnetometer data and we're actually measuring the remnant magnetization of the pipes. So we basically see the ends of the pipes. Okay, so these are all this is basically the ends of all the different pipes as they've got, a dipolar moment, right? They've got a north and a south pole to them. So let's look at the ERT data. Now this is the inverted data because we don't look at raw ERT data. We invert the data to try to model what theoretically it should look like relative to what we measured. We run that through a process called inversion. And these data were really nice and clean. And you can see our depth, we went down to about 13 meters. We get this high conductivity. So now I've switched the scales on you just to make sure you're paying attention. So this is resistivity data presented in terms of conductivity. So we just take the inverse of it. So we can see we're looking at it. We have a really high conductivity zone here. Some other little spikes of conductivity, but everything else seems pretty much similar. The geology is mostly all unconsolidated materials with a little bit of clays. And for some reason, my log did not come through there. Sorry about that. But we took gamma, magnetic susceptibility, bulk electrical conductivity that was collected with a borehole electromagnetic induction log. And we also looked at fluid specific conductivity. So what this tells us is that, okay, we've got an area here of really high conductivity, but it might be associated just with this building here, because the geology really isn't that much different. And the reason why we measure the magnetic susceptibility sort of on the research side of things, because part of that biodegradation model is that we also see that there's an alteration in the magnetic susceptibility in iron-rich sediments as the microbes degrade LNAPL. So that's another sort of physical property change that happens. So the Dualum, remember that was the long yellow EM instrument. We collected that all throughout the site, but this is the inversion of those data right along where we did the ERT line. And here you can see that we've got a little bit higher resolution of geoelectrical property distribution within that near surface. And what we're really seeing is the transition between some finer materials and some coarser grain materials. So this is really helping you in a pretty high resolution to understand your conceptual site model and help refine that. And then since we collected those data all throughout the whole site, we can then take depth slices through that and try to understand how the electrical properties change. And what we find is that in this site, it turns out there's a really clay-rich zone in here that is our interpretation. And then we also have a really elevated connectivity zone, which coincidentally runs really parallel to that utility trench. So we might have some sort of connectivity plume or some sort of alteration that is coincident with those areas. And then we've got from our well logging data, we've got some evidence of that. Yeah, this is really an area that has a lot of fines in it. So now let's move to north central Arizona. This is in Tuba City. This is the Davis Chevrolet site. This is where there was an old Chevrolet dealership here, a couple of tanks that leaked and down into this big property here. And this is, probably a little over 3,000 feet. Here, the geology is a bit more complicated, or here's the map. You can see the map of the plume where we have the high benzene concentrations shown in the lighter colors. And you can see it's sort of moving off into that southeast direction. We basically have silty sands on top of a bunch of sandstone. We're about 40 miles as a crow flies from the Grand Canyon here. And water table is deep relative to the other area. We're about 10 meters down or more. So we did a bunch of ERT lines. We did a bunch of mag, frequency and time domain EM. There's the resistivity data. We did some radar and then this passive seismic and a bunch of borehole work. And this is where we did everything, and you can see where we surveyed. So these are the raw Dualum data, right? That's that yellow instrument. So we can look at the raw data. And if you look at this, you might say, oh, wow, look at that. Here's a huge, connectivity anomaly here and a big low in here. But again, this is just raw data. We've got to correct it for topography, and then we've got to invert those data. And we do, when we do that, we find out that, well, we're really only seeing it down to about 6 meters. This is what we call our DOI, our depth of investigation. So we're not even getting to where that water table is with this method, but we're getting a pretty good characterization of that near surface. And with the other EM instrument, here's the raw data again, but then once we invert it and correct for topography, you can see we have a very nice little layered earth section. But again, that's in this upper like 4 meters or so, and we're not getting down to the water table where we want to be. So looking at the ERT, this is ERT just on this line 1 right here. Here we can see based on our acquisition parameters, we got over 40 meters in depth, and we're beginning to see some structure in the subsurface. Here's the package where the EM data gave us some good information. And as we got deeper, now we're starting to see, there's definitely some geologic or geological structure within the subsurface that might control or guide or help us understand how the plume might be flowing. So we also compare that to the EM induction logs, right, that measure the connectivity with depth. And if we notice here, I've worn out there we go. Here's where the groundwater is, but notice, so this is connectivity with depth. Notice right above the water table here, we're getting an increase in connectivity, a little bit higher here and an increase in connectivity here. So think back to the earlier slide I showed you about the using geophysics to monitor microbial degradation, and that increase in connectivity we saw like right above the water table in that sort of smear zone. So we're starting to observe a similar thing here with the downhole tools, but it's at such a fine scale, we're really not able to resolve it with the surface geophysics. So again, another reason why we use all sorts of different methods to try to get converging lines of evidence. And then of course, so now we can pull together all these different lines as shown here. These are all the inversions. We can begin to see a lot of structure at depth. And we can throw those into different diagrams. And here we can start to see, there it goes. there's definitely contacts and structure here, which might govern the flow. And if you can see this contact here is definitely moving in the south-southeast direction. We also overlaid that on earlier work that was done about 10 years ago. And what's interesting is that our resistivity data, while it went deeper, correlates pretty well with the surface or the more shallower work that was done as well. So we're getting even more lines of data over time that show that, we're helping to aid in understanding the geology and what's going on at this site. I know I'm getting a little bit long here, but I'll go really fast. So we also measured the passive seismic measurement where we can just measure the Earth's natural vibration. And when you measure that in different components and look at the ratio of that and the resonance frequency that peaks, we can compare that to acoustic impedance contrast between solid rock and unconsolidated rock, or if there's an acoustic impedance of about 2 to 1, as it shows here. And we use these formulas to try to calculate what that depth might be, to try to understand what the depth might be to bedrock or not. This is what the data look like. So here's the resonance frequency. You can plug it into the formulas, and we can come up with depths and plot it on our site map to try to get an idea of where that acoustic impedance is falling. And then we can compare that to the other data. And what we found was that the passive seismic found this interface between the silty sands and the sandstone, and just further refined and helped us understand what that EM data was telling us at that site. And lastly, so in summary, we used those different geophysical tools to help develop converging lines of evidence to understand the site and understand what's going on in the subsurface to help make future directions or decisions. Sorry. And I wanted to really quick go through some online resources that we have at the EPA that are about to come out, but we've got a very thorough website coming out on environmental geophysics. It goes through a lot of different resources. It essentially is an online geophysics textbook, as well as a bunch of free software tools that are available. We go through all the different geophysical methods, surface, borehole, and waterborne methods, the different physical properties they measure, and case studies. All sorts of stuff is in there. There's a list of references that we try to keep updated. Was last updated in May, but it's all different resources in the peer-reviewed literature that have geophysical applications to environmental problems. And then there's a bunch of decision support tools. We have a fractured rock toolbox, groundwater surface water method selection tool, all sorts of different geophysical software utilities to try to, we can estimate Archie's law response to different sites. And then also we've got some forward models where, in particular, I wanted to point out the scenario evaluator for electrical resistivity, where you can enter in what you think your geology is like, if there might be a plume or not. You can experiment with acquisition parameters, and then it'll predict based on what we know about the physics and the math about what the response should be. So then you can guide investigations or say, okay, is geophysics going to work at my site or not? How can I be most informed prior to going out in the field? And then we've got inverse models too that are available, and this is constantly growing. So anyway, I went a little bit long, but that's your geophysics indoctrination for the day. And these are all my collaborators. Thanks.
Questions for Dave?
Hi, when is your website coming online?
That's a good question. I know. I was like, it's not quite approved yet. I'm just waiting for approval. Hopefully soon. I'll say end of the year, calendar year is what we're hoping for. But yeah, you saw the there's the URL, epa.gov/environmental geophysics. Hopefully it'll be out soon. My email is probably what was on the front page or my first slide, but I'm happy to, distribute that, and I can keep you posted.
Thank you.
Hi, thank you for your talk. I was curious, how long did the field work take for each of those respective sites to perform all the geophysical methods?
So the last two sites in Havasu and Tuba City, we spent about, Havasu was a little bit smaller. I think we were there about 4 days. Tuba City is a much larger site, so we were there for 4 or 5 days. Lauren was there. She can confirm. So that's about it. Yeah, it was a 2-week trip. We spent essentially a week in each place. Big weather difference too. We were at Havasu, it was like 90 degrees. Tuba City, we're in snow. After a 5-hour drive, yeah.
So I'm curious, when you do these research projects, how do you determine what sites that you're going to do this research on in terms of,
Right.
are they public sites? Are they Superfund sites? Are they?
Yeah.
How do you get on the list?
Talk to that guy, talk to Alex right there. So EPA works, so I'm in EPA's Office of Research and Development, right? So we work on like a 5-year research cycle where other offices and regions in the EPA like will tell us, you know, these are our problems. And so I look at it and say, oh, geophysics can help solve this problem. So then I'll get research funding to do that. And it might be just basic research, you know, where we might just do bench scale lab stuff, or it might be more applied to where like we're past that stage to where now we're looking for a site. So then that's when I go to the regions or Office of Underground Storage Tanks and say, you know, hey, I'm looking for a site. Or they might even come to me and say, hey, we're having trouble with this, could geophysics help? So, you know, that's sort of how it comes together. Both those sites are tribal sites. So I try to, you know, if I'm going to test different methods or have a case study, I try to find, you know, sites that really need help, right? Or that I think I might be able to help. I don't know if that answers your question or not, but yes.
Hi, yeah. After hearing these talks today, it's kind of screams that we need some cross-discipline exchanges with microbiology perhaps. And I was just curious, maybe the geophysicists are already on this, but for example, diesel fuel is highly labile. Microbes love it. And long-term, they generate metabolite plumes from it, which are probably, conductive.
Mhm.
Whereas gasoline does not generate those metabolite plumes because it doesn't have a lot of metabolites associated with them typically. And so there's a lot going on with natural source zone depletion and the degradation patterns and microbes, as well as in the RNA, DNA, and then soil gases indicating. So I'm just curious about, maybe next time instead of a geophysics, it should be a microbiology affecting the CSM. But are you guys investigating these overlaps, and what are some of the research areas you're thinking about?
Yeah, so the whole microbial response or the geophysical response to microbial activity in the subsurface, that was actually a lot of work. I did a lot of that work in the late 90s during my PhD research. And that research has continued, but there was a lot of collaboration between a lot of microbiologists. And that is continuing now. I don't have any funding for that to continue it right now, but that's really grown, and you're absolutely right. Yeah, because as I said before, as geophysicists, we're just measuring the physical properties of the earth. The mechanism behind what that physical response is a, as we say, it's a biogeophysical response, right? So there's all sorts of different metabolic pathways and geochemical alterations that occur that, is ultimately what we measure geophysically. But yeah, you're absolutely right. This is, geophysics is just, a hammer or a screwdriver in your toolbox, right? And you need to use all your other tools and all your other disciplines to try to understand what's going on.
You guys want to weigh in on that?
Oh, I've got this magic. The trick I found for the microbiology side is they go, oh, that's really cool. Why don't you bring it in a lab? And the thing that's really cool is their structures that they're building. It has a form to it, and the biologists call that studying form. And we need to do some studies of form out in the field of why did they grow the way they grow, and why did they put a root in a particular place? They'll also put up little chimneys up to the surface. And what are they thinking, or what are they doing? And you can't capture that in a lab. And so I've been trying to get people funding or studying the form that we're seeing which is a way different question than, are they present or what are they degraders? It's like, no, they're building an entire colony that's doing something and transporting things. They also have a signature where they get more conductive than their body parts can be. There's a hypothesis that that's when they build a biofilm. But those questions aren't answered, and it's something that you're going to answer in the field, not in a lab. And so getting field-based microbiology, tackling what signatures we're seeing, I think is the direction you want to go next.
Yeah, there's been some in the early 2000s, there's been work looking at biofilm, like using different geophysical methods to identify the biofilms, and that shows a lot of promise too, yeah.
I was just gonna ask, what, can you give us ballpark, cost estimates of what you had to get in terms of funding for those two projects?
Boy, I'm hesitant to do that because I'm not out in the private industry charging things and understanding. I mean, maybe Todd can answer that better. But yeah, I don't really, I think it's region dependent and stuff like that. But these, the big suite of stuff that we went in, like, that was about a week's worth of work, and then probably, 3 weeks worth of data processing. So depending on what your billable rate is.
This is more of a comment than a question to address something Todd just hinted at, but there is a talk tomorrow by Dr. Ed Winter addressing some of those microbial differences from both field investigations like we've talked about here to differences in the lab. And we're actively working as practitioners to marry those up, but he's got some really good data. I think he's got some quant arrays, some other field scale data, some lab scale data to show you the differences that occur when you do pull it into the lab and the deficiencies that sometimes occur in these CSMs when you only look at it from a lab perspective. So I think that's a cohesive way that this conference is doing something really good for us in this industry, but talks directly to what you just mentioned, Todd, tomorrow. I think it's tomorrow, right, Nathan?
Maybe a round of applause for all the three speakers. I know it's almost lunchtime, so I'm not going to take a whole lot of time, but please make sure that if you have not filled up the evaluation form, you do that and give it to us. Your feedback is very important. And